robot Sparql query tutorial, just a basic thing, so that everybody's in a position to use the command line to query FoodOn for contents. And then we can add some of the more useful queries we come up with onto the FoodOn website. Last week, one of our users asked if they could just have a tab delimited file of all of the FoodOn food labels and their synonyms. So I remember doing something like that in the past and hadn't updated that query in a while. So what I'm going to do is share screen and just work on that today. But first, does anyone else have any pressing items they'd like addressed, whether it be issues or other questions or needs? Okay, so all right, Megali. So the screen share. Okay. Good. So what we have, and I'm pretty sure, so just in terms of the agenda, I had mentioned one thing, show logic error for Kebi role and placed under BFO role and protege. And so I'll do that at the end. I'm sure we'll have time for it, but I was just working on Sparql querying. So, so I guess the first thing to say is FoodOn is an OWL ontology, and OWL is constructed to be compatible with RDF, the resource description framework. And RDF was invented about 2000, year 2000. And it's a format of expressing all of the data in triples, the subject, predicate, object. So when you break open an OWL file, look at it and look at all the different statements that are put together to create these hierarchies of terms and all of the axioms. They're all written in a file, in a format that can be converted to triples in a triple store database. So when people talk about graph databases, there are two kinds of graph databases out there. They're the RDF triple store graph databases, and there's a good standard around those. And then it's a bit of a Wild West when it comes to the other kind of graph database, which is I'm just say predicate, but a relational database, which is a logic predicate. Yeah, not predicate. Sorry, I'm mind blanking, and I do this occasionally. It'll come to me. But anyway, the Neo4j is a property graph. That's it, a property graph. And the way, just very briefly, the way RDF graphs are different from the property graphs. RDF graph looks like a property graph in that you've got a subject, predicate, object, and the predicate is what the property graph people call a property. The difference is with Neo4j, you can actually annotate all of the properties with extra stuff, whereas you cannot do that with RDF. Now, that may have been just, going over some people's heads. All I just mean to say by that is that when we talk about Sparql querying, Sparql is designed for RDF triple store graphs, and there are other languages out there for the property graph family of graph databases. So here we're just choosing to work with Sparql, and that means just the RDF graph that's much more native to what the OWL format has going in terms of querying. Okay, so first, any questions about that 20,000 foot view? Okay, so diving into the Sparql querying, one of the nice things about Sparql queries is that for the databases that are compatible, you can query them via endpoints on the web. And so I dropped a little link to what looked like a very promising Sparql endpoint here. And so the EMBL EBI, European Molecular Biology organization, is a pretty big powerhouse in terms of sequence repositories, DNA sequence repositories for all sorts of living and dead creatures. And so they have offered not only a platform for the OLS ontology search service, which is accessible, which I presume you guys all use, but here's the OLS interface for searching ontologies, such as FoodOn, but they also offer the Sparql endpoint. At least they did until I learned this morning that they no longer fund this. This is no longer funded. So this Sparql query endpoint, which was so promisingly looking like it could query particular ontologies and get back results, when you submit the query, you will get 0 results. And I just learned that that's because there's no more funding for this, but it would be really helpful if they said so on the website. At any rate, with other places more popular like Wikidata, you can get a little box where you can put in your Sparql query and press a button and get results, not only from the databases that are right at this endpoint, sitting on the server where this Sparql endpoint is offered, but often Sparql enables federated queries where you can issue a query in one Sparql endpoint, but it will go off to other Sparql targets and collect records from those resources. And Wikidata really shines in that respect, tying together different databases. So we're going to use Sparql, and we're going to use it directly on the FoodOn OWL file. And to do that, we don't have a Sparql endpoint set up in the website like this yet at the Shao Lab to work directly with a mirror of the GitHub, the FoodOn repo. So instead, I'm just going to use the command line to run Sparql queries. And the kind of Sparql query we can run can be provided in a little text file that we run on the command line just by using a tool for running Sparql queries against a particular OWL ontology. So to slowly lower ourselves into this is to look at the basics of a Sparql query, and then at the context of running it in the command line. So Sparql queries are, and I'm not an expert in Sparql queries. I haven't really used them to query multiple databases and bring back stuff, but I have used them a fair bit on FoodOn and on a couple of other ontologies just to pluck out terms from that ontology. So at its default, when you run Sparql, you're running it pitched at a particular Sparql database resource of some kind of triple store. And what the command line robot tool is that we've been looking at in the past just to convert tabular spreadsheets into OWL files. Well, robot has another command called query, and that stands for its Sparql query engine. In robot, you can tell it to query a particular OWL file as though it were a triple store database, because that's what it is once it's loaded into memory by robot. And you can specify with the -- query attribute a file that contains that query, a query. And so I've got a simple example of that, this owl get labels.sparkle. I think it's in the memory here somewhere. Let me just see. Precise. Here. So query input FoodOn merged. Owl, query owl, get labels, and the output is this test.tsv, and we've asked for it to be a format of TSV, but you can also get robot to output JSON and so on. But since a user last week wanted TSV, I resuscitated this query from the past, and it's pretty simple, this one. So let's talk about the guts of a Sparql query. So first, any questions? Okay. So I guess I'll just say one other thing, robot. So this robot doesn't come with your Apple computer or your your Windows PC or Ubuntu computer. You have to load this software. There's mentioned it before, but the robot library.org website talks about how to load this tool up on your computer so that you can access it via command line. And the so here's the instructions on how to get it onto your computer. And you'll see that it's a Java program, robot.jar. So you have to have Java running on your computer as well. If you have any problems with this, you want to use this tool and you have any problems setting it up, let me know and I'll try to bumble through figuring out why it's how to get it going with you. Okay, so in terms of queries, this is a very simple query, and all the queries in the robot in a OWL pitched against a triple store can use abbreviations for some of the elements of the triple store representation. So here we're looking at a triple. This says some variable for the subject of the triple and a very particular predicate or relation between the subject of the triple and the object. And here's a variable for the object. And this is a select query to select all distinct things, subject and label together, where the subject is a label, has a label and that label. So this query is going to bring for any ontology every single label of every single entity in that ontology. We could have named this ontology the or entity, and we would get the same result. So it doesn't really matter what the variables are, but the variables are given away by the fact that there's a question mark in front of them, whereas the predicates or other references to constants, to particular terms, won't have a question mark. They'll usually have a little namespace prefix. And so that's the last detail here. You can use these abbreviations for the prefixes or the beginning URLs of your triple store content. So let me bring that down to earth. Basically, this prefix is a shorthand for typing in this big long URL. When I go look up what a triple store predicate is, I will get a full label sorry, a full address or URI for that. So let me illustrate. If I go into Protege right now and I'm looking at FoodOn, and I'm looking at any particular term here, and I hover over it, I will get the URI for that term in its full form. So the prefix in this case is FoodOn, and the longer term name is perl.obolibrary.org.ovo/foodon underscore blah, 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 blah. Okay, so that's the full resolvable Perl. I mentioned the word Perl permanent URL, the full resolvable address for that term. And that literally means that I can take the IRI or URI is pretty much the same thing. Go to a web browser, select it, and get this entity looked up on a ontology lookup service online. And this is Perl. It's a Perl because it's expected to stay around for eternity. Okay, any questions about that part? So an OWL file is a combination of these Perls for the terms and the Perls for the relations or the annotations between them. And therefore, back in Protege, which is a handy tool for looking at the terms and their Perls, I can go to annotation properties and see one called label, and look up what its address is, and see that that's the address, and see that that's the full address of the thing that I'm trying to access here for the label of the term. But since it's such a hassle having those long addresses, we can use these shorter terms. Okay, so we'll just mess around with a few more of these annotations in the query. So here's query, and it's sitting in the text file. Make sure it's saved. And now I'm going to run it. We're querying FoodOn merged, just because FoodOn merged is a single file that has all of the FoodOn parts in it, including the NCBI taxonomy and a number of other ontologies. Robot is intelligent enough. If you just queried foodon.owl, it's intelligent enough to go off, I think, and get all of the imported files that FoodOn also includes. But using FoodOn merged is just a faster way of querying the OWL file content and getting it loaded up into memory by Robot. So I'm using that input here for speed. So it's run. I told it to output this test.tsv. So here's test.tsv, and it's over 2 megabytes in size. If I go less, Linux command for listing text files, less test.tsv, I get the contents of it. And it's just got ontology ID and label. And it's returning every ontology, every term entity in the ontology. It's returning its ID and the label. You'll see that the labels are quoted, and they have this little @en, and that stands for language tag. I've been trying to code all FoodOn terms to have the language tag, but you'll see that other ontologies don't necessarily have that. Here's NCBI taxon, and it doesn't have an en language tag at the end of it. You can see they're, in this case, these are Latin terms, but I think they're generally shying away from language tags. Here's Kebi, cetanoic acid, and it looks like Kebi actually has a version that has the language tag and one that doesn't. So that's something just to be aware of if you're consuming this data. Right, so the user last week said, I don't just want the label, I want the synonyms. And to get synonyms, we have to actually start querying for some other attributes. So first of all, any more questions about this?
I wonder if there are any other like special packages that I'll need to install for doing this.
Right. So when you install Robot, it needs Java, but I don't know, are you on a Mac or PC?
It's Mac.
Mac, right. So Mac should, I think, come loaded with the Java that will run with Robot.
So Robot is the only one.
Say again?
Is Robot the only one that I'll need to have?
Yeah.
Okay.
And the reason is they inside Robot is what they call the OWL API, which is a standard library for reading text files that are ontologies or other RDF databases.
Okay, got it. Thank you.
Okay. Yeah, if you have any issues getting Robot to run, let me know. The other thing is, Emily, I don't know if you've been using GitHub before. Have you? I presume you have.
Yes. So I've been mostly doing Python.
Yep.
And a little bit JavaScript. So like not really Java before.
That's fine. You won't need to know a thing of Java. Robot's written in Java, but we don't mess around with Java at all in any of our work.
Okay, great.
Okay. But just in terms of GitHub, the easiest way to consume and look at FoodOn files is to use GitHub Desktop and clone the GitHub repo for FoodOn, and then you'll have a mirror on your computer up to date of all the FoodOn files, including this FoodOn merged one that I'm talking about here.
Okay.
Okay, so if you need a little hand with getting GitHub Desktop going, you can let me know.
Okay.
Okay. Yeah. All right. So so we just looked at this one label annotation, and just to remind everybody, in Protege, when you're looking at the default windows that Protege gives you to view an ontology like FoodOn, it will give you this entities tab and maybe one or two of these other tabs. And the hierarchy of the ontology, it can be explored by opening and closing items in Protege in this entities tab. Entities and classes are pretty much the same view. I won't get into the difference. You can use either, but the thing is, the views on these tabs are that they provide other sections that talk about the annotations that are applied to each term, and then the logical statements. So all of my talk today in terms of querying is just about these annotations. Annotations play no role in the logic. If you run a reasoner, the reasoner doesn't care what your annotations are, definition and label. Let's look at this is kind of a good one. Fruit from the plant ontology. The annotation part is filled with things like the label, an ID, alternative IDs in, for whatever reason, the definition of the term, comments. See also, all of these annotations are extra bits of information, and they show up in triples, and the predicate that we're talking about that attaches them to this fruit entity is the one listed in blue there, the annotation itself. So if you go and click on the add button, you will get a list of these annotations, and these are all viable as the middle predicate that connects the subject and object, in this case, and term by its ID and the given annotation. So we're interested in annotations about alternative term. So there's an IAO information artifact ontology URL for that. And if I wanted to bring in alternative terms, then I would need to get that that alternative term identifier, or the URL for that thing, and bring it into the query. So I'm going to do that right now. Alternative term isn't used very much, but it is used occasionally. And so I'm going to just switch to the mushroom query because it already has reference to this optional IAO annotation. Okay, so I'm going to bring that in. And save it. And I think I might get a little error, so we'll just figure out what that is. So, so this adds one other aspect to Sparql queries, which is that you can demand that what you're looking for has a certain structure. There's no optional aspect to it, but you can also add on that there are other things that you're also interested in. So I'm interested in not only a term's label, but its alternate label. And to get that back. So here's an optional. Now that we'll go take a look to see if, for whatever ontology ID was chosen, whether there's also another relation, this alternate label one. So let's see if that runs. May not run if I need to add another period or something to the query. Okay, OBO IAO 1118. Right. So in my query, I defined what this prefix is, but I forgot to define what this OBO prefix is. So I need to add that prefix. Tell it what OBO is. And I could just as part of that. And run it again. Okay, and without a problem. So let's list the results. So now there's an alt label field. only problem is it's going to be tough to spot where the alt label is because it's the third column, and almost nothing has alternative labels. Very rarely is that used. So I'm not going to try to find an example of the alt label, but instead we'll get some other fields in here that are important. Okay, so the last thing to say about this particular example is that you can select a bunch of fields, just like with SQL, on one line for the output. But where Sparql is a little bit different is that it will, its search algorithm for finding optional things means that if there are several optional things, it's going to devote a separate line in your query to each one of them. So strategy to handle that is to move to what's called a union query. So I'm just going to move to that because that's going to be provide all the synonyms in a better fashion for our needs. So I'll leave that query as it is and shift over to the mushroom one. This adds just a little bit more complexity in the mushroom one, but I'll run it to show. Let's see. Fill up the time here. Mushrooms, okay. So I'm running this FoodOn against FoodOn merge. I'm wondering this owl get mushroom.sparkle. And if you'll note that this is an existing query that's right in the FoodOn repo. So let's see what it delivers. We'll take a look at the results and then back at the query. Okay, so it starts off with mushroom whole organism, and then is spitting out each of the labels of just the organism section of FoodOn. I mean, just the mushroom section. And then it's got a couple of other high-level terms. So the query is doing two things. It's going and I'll talk about it right here, back here. There are two chunks to this query. One, it's getting all the parents of a given term, and then it's getting all of the children. And so the parent part is on one line and the child part is on another. But first you have to explain what this bind thing is. So we're selecting a distinct set of results with the ontology class identifier, its label, and an alternative label like we did in the last query, this line. But the very first thing it's doing is binding a particular FoodOn ID. And if we take a look at the query, that's actually FoodOn 1287, so mushroom whole organism. It's saying, let's make this term ID as the place to start searching for our contents. And this is doing a subclass of search to some parent class, but not just one parent, but all of them. This is a recursive little star. If I take the star out, save the query, and run it again. Well, first less.tsv has got all of this stuff here, which is actually a path from mushroom all the way up to the root of the ontology. I'm just gonna run it again, and we'll see that that part of the query is gone, except for one immediate parent. Is this level of detail useful for you folks in terms of Sparql? I think most of you haven't used Sparql before, right? Right. Okay. So it is the language for RDF querying of triple store graphs. So yeah, this should be useful in the future for this grand vision we have of tying together all this data across the web using Sparql. So here we go. Less.tsv. So now we are just getting yeah, we're not even getting the word mushroom in here. We're just getting all the children of mushroom. And actually, it looks like I could do a star here. All right, so let me explain. The mushroom term should have returned its parent, and I think it did. Basidiomycetes is probably the parent of the mushroom at the moment in FoodOn. And in fact, how about I go get our bearings by opening up FoodOn 1287 in FoodOn, right? So here's the mushroom whole organism. It is a FoodOn grouping because the word mushroom covers quite a number of things that taxonomy doesn't quite organize in the same hierarchy. But we have put it under Basidiomycetes, and that is all right, the FoodOn version of that. And underneath are the various mushrooms. So we're seeing Basidiomycetes, the parent, and then all of the children as a result of the Sparql query. And that was with the query in this format. I can get rid of this fancy union stuff and just focus on all the children. And now there's no Basidiomycetes, just the children. This plus sign says, find me at least a subclass of, and then maybe a subclass of and a subclass of that, or a subclass of and a subclass of and a subclass. So it's equivalent to writing over and over again another expression which allows you to put paths and linking one entity to another through various levels and relations. So this would select only hypothetically for any ontology entity ID, term ID, it would go and find not only the child, but the grandchild and then the great-grandchild of, or actually this is the other way around. Subclass of means that the term is underneath another term. And so for the search term of mushroom, find not only its immediate child, not only its immediate grandchild, but its great-grandchild, and only those. So only those terms that are 3 levels deep if I didn't have the plus sign there. The plus sign is a way of saying add one or more of this relation. If I just did subclass of like that, we would get only the immediate children of this mushroom term. So less terms, and they're all immediate children, but none of their children are listed. And yet a number of these items do actually have children in them. So we're not getting any of the children anymore. Sparql oyster. We'll just be getting oyster mushroom genius somewhere right here. Okay, so if we wanted to get not only all children, all grandchildren, we would use the plus sign. But here, if I use this asterisk, that means attach 0 or more instances of the subclass of. And so if I'm not mistaken, this should get us the mushroom class as well as all of its children and great-grandchildren and so on. So let's run that. Yeah, fine. And once we've done that, now we can start playing with getting synonyms. Right, so that using that star has now given us the term itself. The search term is now being returned as class, as well as 1 or more, all of its grandchildren. Okay, so let's get some synonyms in here. I'll do that by adding the annotation for synonyms. So we have different kinds of synonyms: broad synonym, narrow synonym, and exact synonym. And in Protégé, it's a little bit tough to see exactly what the IDs are for these. You don't get any mouse over. Oh yeah, well, it's indicating what the URI is for each of those. But I want to cut and paste that. And there's only one way to sort of get a cut and pastable link, and that is to select the annotation and then go up to the menu where it says refactor, rename entity. This is the only way in Protégé to actually get a way of cut and pasting the URI for that. So I'd like to get a synonym, but I don't want to be using these big long names, so I'm going to use prefix again. And this short prefix for this ontology namespace is called oboe and owl for all of the prefixes. The format is that this long string gets substituted in for oboe and owl. And that way I can say oboe and owl has broad synonym. I can put that in as an optional thing to bring back. Since not all terms have broad synonyms, but some do, we want to make it optional. Okay, so adding that, let's see what we get. Okay, so now we're starting to get some broad synonyms that cover more particular terms. So it looks like there's 2 broad synonyms for this Scotch bonnet. Now that might be something worth questioning. Maybe this was mistakenly marked as a broad synonym, and it should actually be an exact or narrow synonym. That gets into the discussion of how we're using synonyms in FoodOn, but I won't dive into that here. Just to say, let's go find out what the narrow and exact synonyms are. As well, people, including FoodOn itself, use the word as synonym without differentiating whether it was broad or narrow or exact. And that was because when we imported from Langual a lot of these synonyms, we didn't have the time to question more particularly what kind of synonym they were. So existing Langual records have this has synonym, but we need to differentiate them into has broad, has exact, and has narrow. Okay, and we need to return those in the query too. Synonym, broad, exact, and okay. So now tons and tons of data. But what do we run into? We run into repeated rows. The rows are just coming back with every permutation and combination. For spicy night mushroom, we've got all sorts of synonyms, but they're taking up separate rows due to the Sparql search algorithm to go find optional parts of things. Much better that for one main entry that we would just get a merger of synonym terms, perhaps for some kinds of user that just want that, or an indication of the type of synonym, and then the synonym on a separate row. So I'll do the first part of that. We're running out of time here, but I'll do the first part of that adjustment so that we don't have a big, long set of columns. We just have more specific ones. So it means using this union structure. What we want is indeed all of the subclasses of our search. But then we want for each, we just want to return a for each class, we want to return one row and just one entity. So it's going to be a kind of union, and actually I'm not going to try to guess this right in front of you. It's going to probably take me 10 minutes to figure out the best way to add a union. I think maybe, well, take a first stab at it. We want one of the things to be the label, and we don't need to make it optional anymore. And then we'll do the same union. That's the first query, and then we're unioning it with the next query, which will be just like it, except we're looking just for has synonym. Union. Has broad synonym. And so on. So let's just run cream it. We'll run this query, which is a union of everything with a label that has synonym, and then it has broad synonym, and that all being put into just this label field, so we don't need all of these other labels anymore. But they're going to come in on different rows. And the sorting won't be particularly nice, but we can solve that later with an ordering. Okay. So I'm expecting to see in this list, I think I better just make it easy on myself, order or sort. Is it sort? Let's see, is there a sort? I'm just skipping over to the FoodOn website where order by is the last thing I need in this query. Order by class. Let's run that one. See if we're getting any synonyms in here. And that should wrap up the demo. The last thing we'll want to add is the sort of constant that says what kind of synonym a thing is. Right, so here's one. The field mushroom is also has a, oh no, sorry, different ID there. Okay, you know what? I think there's just so many exact synonyms, not as synonym. Let me just try another union here. Oh, I know why I'm not getting any results. This RDFS is not the prefix. These have to be oboe and owl. That's what the prefix is for as synonym and has broad synonym. And I might as well just throw in the as exact synonym, which is what we're trying to move all of the synonymy to. And then we'll be in a position to add one last thing to differentiate what the synonyms are. Okay, there we go. So for this Cantharella siberius, there are all of these other synonyms, broad, narrow, and exact, but we don't know what kind they are. So the best thing to do is add a field to the results, syn type, and in each of these, bring in I believe it's something like this. Find as some question marks and type. The bind is just a way of binding constants, identifiers, and values and strings to variables. And so this one would be a synonym. Synonym. Exact. Let's run that. Hey, great. Label exact synonym, lots of exacts. That's good to see. Right on. Good. So this is, I'm going to put this query up online on the FoodOn website here in this reuse technical. I'll put it up at top and as well keep a link to this file and keep this file refreshed more frequently as a result of the build process so that we can get all of this synonymy and labeling up to users right away with new releases. And that brings us to 9 a.m. And so I should stop the video. Any questions about this so far? No? Okay. It was...
Magali speaking.
Yeah.
Once you've got the TSV file, you have to save it and then you can use it.
Yeah, that's right. So this query, this robot query is saving the TSV file and by that test.tsv name. This is the source directory, ontology directory of the GitHub repo. So test at the moment is being dropped in here, but I'm going to create a make this the output for FoodOn labels that just sits there. But I think actually I'm going to move this. Maybe it's called FoodOn labels or FoodOn synonyms. I'm going to move it to be a permanent file on the GitHub repo in the root directory. So it's really right in front of people's faces. So GitHub, FoodOn. Right now, all of that work that we were doing with me on the command line, I was doing in this folder right here. And that's where these mushroom queries and so on are, label queries. And this very old file, it's 3 years old, haven't touched it since then. I'll make a very fresh version of this. And I think I'll keep the FoodOn labels the name, but I'm going to copy it in the build process right up to the FoodOn source. So we'll have FoodOn labels right up here.